Welcome everyone to another episode of Kiwi Talks. I'm honoured to be speaking to Associate Professor Jan Elridge from the University of Auckland, expertise in astrophysics, stars, you know it. Jan, how you doing?
I'm fine, thank you, Reese. Yeah. My background gives it away about what I'm an expert in, I guess.
Yes. Although with astrophysics, I mean, it's so broad of a subject, right? You can spend a lifetime just focusing on one thing and you'd still hardly know anything, I bet.
Yes. I mean, so I've just had to write a review about the stuff I do, and it's just like you end up, the last bit is just, this is all the stuff we don't know. We know these things, but these just mean we now don't know all this other stuff. And that's just, you're right, a tiny little part of everything in the universe. And so it's what makes it fun.
Yeah. So I suppose week to week, you're always learning new stuff?
Well, you'd think so, but no, sometimes it's just you're chugging away. You have this thing you want to do, you know. So, I mean, let's say you want to understand what a galaxy looks like. Right now, you can go and look in a telescope and look at a galaxy, but how do you understand what the stars are within that? And so, you know, you have to go and make a model of a star, and then that's one thing, but then you've got to work out what those stars look like as they're at different ages, you know, because some stars can be hotter than the sun, some can be cooler, and then you have to add all those models together to make a model of a galaxy. And, you know, there's all these little steps you need to do, and each time you do another little step, something you don't know can like make your predictions much more uncertain, and all these little uncertainties add up. And so, you know, also doing all of that takes a long time. So for a lot of time, you're not making any big discoveries. You're just finding, okay, now I've got something that looks like the sun, which is always a good thing to check, right? Does my model of the sun look like the sun? And then you try and do it. So a lot of the time you're doing all this work, and then it's not until you get to the end point, then you can actually go and understand those galaxies, because then you understand what they're made of. And so at that point, you actually get to find exciting things. But then sometimes something interesting happens. So I did this. I made a way of modeling what a galaxy looks like. And then I didn't think about other things, but I'm always trying to think about many different things. But in 2015, this detector called LIGO detected two massive black holes merging, because it's like these two things that are many times more massive than the sun whirling around, and it's like it churns up space-time. And they was able to detect these things called gravitational waves, which are the gravity equivalent of light. And I hadn't thought to go and see, I've got binary stars in my models. Maybe they produce black holes like this, and they did. And so that was quite exciting, because in the space of a few weeks, we went from not ever having looked at gravitational waves before to trying to predict all these masses of black holes, and having a way of making sure our physics that we've all done before was correct, because there was a new observational window opening up.
So I suppose one little thing being different affects the whole model?
It can do. Well, this is part of the fun of what we're trying to do now. It's like, okay, we can put our best guesses in, but how good are our guesses? And it is that question, like, which is the one thing that we change it a little bit and everything goes wrong? Because then that means we know that piece of physics much more accurately.
Yeah, because if you're starting with data that's incorrect or partially incorrect, and then you go further through time, then doesn't it become even more off in terms of how correct it is?
Yeah. No, it's like predicting the weather in some regards, right? You can predict the weather maybe tomorrow, but predicting it this time next year is much more difficult. So it's exactly as you've said, you know, as you go over time, your uncertainties become much more much bigger, which is, you know, why you want to use constraints that tell you something about the end of a star's life. And so when I started my PhD, which is about 20 years ago now, which is a quite scary thought, I was looking at supernova progenitors. So supernovae are a star that explodes, and it outputs about the same energy as the sun will over its entire 10 billion year lifetime. And so in a few days, you get all this energy and light released, and they're really bright objects. The good news is our sun will not explode in a supernova. You have to be about, it's good for us, right? But stars that are about 8 to 10 times the mass of the sun will get to a point where they can't get energy in any other way, and they cause collapse, forming a neutron star or black hole. That releases a lot of energy that makes the star explode. But, you know, that takes millions of years to get to that point. So it's as you say, if you're more trying to model a star from its birth to its death, if you look at those supernova progenitors, and you can actually get your model to look like those stars that explode and reproduce the explosions, suddenly you realize you actually know quite a lot. You know, you're not as hopeless at this as you thought you were. But there's other things like these black holes that I mentioned. The fact that they're actually so massive, that's like another thing, because there you've got to evolve all your star over its entire life, model the supernova, and know how big the black hole can be made by your star when it's dying. And that's a really sensitive test as well. And it's kind of funny that these are the things that everyone's concentrating on now. And so we know we can get those, but then we're actually looking at the rest of the life of a star when it's still living before it's dying. And now we're getting confused because there's little things popping up here that are actually earlier in the lifetimes. So it's a bit of a mess, but we know something, just not everything.
Yeah. So how do you have that attention to detail? Because you'd become a bit of an anal retentive, wouldn't you, when like looking at the finer details of everything and trying to not lose focus? Because if you're off by one little thing, then it affects the whole model.
Yeah, which is funny because some people say like, oh, you've got to change this parameter by a factor of 10. And it's just like, well, no, we can't, because that'll really make things very different. And so that's one of the things with the group and the project. So I have this code called BPASS, which stands for Binary Population and Spectral Synthesis. And it does this thing where it basically makes a model stellar population, and we can make model galaxies, and then we can compare them to observe real galaxies. So we can do this kind of stuff of comparing models and observation. And yes, we do get a bit, we have to be quite careful. But what we've tried to do is, rather than just trying to match one thing, like supernova progenitors, we've tried to do everything at the same time. And so it's more like trying to spin plates. You spin plates on a pole, and you've got to keep on spinning them, because if you change one little thing, everything else goes out of whack. But it's really fun because now we've got to the point where we've got lots of students and postdocs working with myself and Elizabeth Stanway, who's another associate professor at the University of Warwick in the UK. And so it's quite good because there's so much to do. We can say, here, we've got these models. Here, go and look at this. And so it's actually quite exciting because all the different students, they can all talk to each other, and they can all go, okay, we're all using the same models, but we're looking at them in different ways. And that makes it quite exciting. So you don't actually have to worry about the details too much, because you've got students to try and work out what's going on. And actually, it's really interesting seeing them talk to each other and share ideas and solve their own problems. And then we actually learn quite a lot from the ideas they come up with.
Oh, that's cool. So how long does it actually take to create a model?
So which one?
Well,
because there's multiple levels.
Anyone. Well, okay. Give me the most recent one that you've done. There you go.
Okay. So so this is, it's tricky because you've got levels. It's like, can I make my joke about everyone likes layers, like parfait. Everyone likes parfait, and like ogres like layers. So if you need that quote, it's you've watched the right good movies when you were younger. So we've got at the base level, we've got these stellar models, which is where, you take a star, you give it a mass, you give it a composition, and you evolve it over its entire life. That takes about 5 to 10 minutes, depending on what happens. If it's like a really boring single star like our sun, it takes 5 minutes. If it's a binary star and it has to interact with the other star, that can actually take longer time, because the more interesting things that happens, the more computations need to be taken. Now, that doesn't sound too bad, but the problem is to make a model, or to have models that represent all the stars you can have in the universe. At the moment, we need to make about 250,000 of them. So 250,000 multiplied by about 5 to 10 minutes soon becomes something like 10 or 20 years of CPU time.
Wow.
So we only do that once. Because we do those in a cluster, and so we have thousands of cores calculating thousands of stellar models at the same time. So it takes a lot shorter time for us than decades. So when we've got those, then we can do the other things on top. So then we can work out what it looks like. And those used to take a day, but now they probably take a couple of hours to actually compute through. And that's just because hard drives and computers become so much faster. But then sometimes we're trying to create, like compared to a new observable, like when we was trying to compare to those gravitational wave events from merging black holes, we had to go back and actually think, okay, how do we actually do that? So we actually had to create a new model. And those ones are so complicated because of you have to take a model and change a parameter slightly each time. They were taking up to about a week. but now they've come down to about a day. So you're constantly having to try and make the models, but we try and keep them short. And the students normally come up with something that maybe takes a few hours to a day compared to whatever they're trying to, observations they're trying to get.
So, with black holes, when you see stuff in films or you read about these theories, do you ever roll your eyes? Because in terms of, like, say, Interstellar, or there's a wormhole on the other side, I mean, how plausible are any of these things really?
Okay, right. So, number one things, wormholes in theory are possible. Although, so actually none of this just winds me up, right? This is all just a teaching moment, because you can say, okay, you've got these things in science fiction movies, but what are they real? How do those actually work in action? And so with wormholes, they're always, like in the TV series Stargate, shown as like a two-dimensional gateway you walk through. Whereas Interstellar actually got it correct, right? It would be a sphere, because it's a hole in three-dimensional space-time that you would walk through, right? It's more expensive to do that as a special effect than just having a nice gateway you walk through. So Interstellar did okay. And it also had the black hole, that massive black hole that's a million times the solar mass, millions of times the mass of the sun, with the planets orbiting around it. The images of that were correct, which is quite scary to say, because they went to Kip Thorne, who basically wrote the book on gravitation. And, it's interesting because the black hole warps space so much, you can see behind it. So you kind of see this halo around it. And so, the light that's coming off this disk that's feeding the black hole, the light doesn't go straight up, it gets curved round and bent so you can actually see it. So that was all completely correct, which is good kind of fun. The stuff at the end where they go beyond the event horizon and they have to get quantum gravity, that's a bit, yeah. But, you're trying to tell a story, and, you can see this in Star Trek and other science fiction. They go to where the bounds of knowledge are and they try and make something that sounds reasonable. The real problem is other movies where they just throw reason out the window. And my favorite example of that, unfortunately, is a movie called Sunshine, which is a great movie where they're going towards the sun to try and reignite it, start the nuclear fusion reactions. And all of that is fine, apart from the horror movie at the end. Never mind. That's the problem. Space movies sometimes, like Sunshine and Event Horizon, just become horror movies because space is interesting enough. But in Sunshine, it's why the sun is dying. And that is the one piece of science fiction that really gets me going. It's just, if the sun was going to suddenly die, we would see other stars like the sun suddenly dying in the universe, and we don't. And there is no astrophysical reason why it happens. They had to hire a particle physicist who comes up with a really silly particle physics reason why the sun was dying. So the sun won't die. Sorry, that got me away from black holes.
That's quite all right. I'd imagine it wouldn't be hard for you to watch a film anyway, any type of science fiction film that involves space and stars and stuff, without you just being so analytical and critical of it because of its inaccuracy.
Well, I try and always take the view of, how could this work, right? So in my lectures, I always use the science of science fiction, because it's a way everyone watches science fiction. If you go and look at my PhD thesis in the acknowledgement section, there's a paragraph where I actually thank a large number of science fiction authors. And, because I grew up I was born the same year as Star Wars. I remember going to see Return of the Jedi with my father in the cinema. I watched Star Trek on Wednesday afternoons coming home from school, and Star Trek Next Generation, and Doctor Who on Sunday mornings, because it was after it had been stopped. But I watched all the series. So that's one of the reasons why I'm an astronomer, because being an astronomer is as close as you can get to being Doctor Who, right? You get to travel around the universe, understand it. You get to take young people, teach them how wonderful the universe is. Fortunately, there's not that many Daleks to try and kill you. But there is still quite a lot of running, because that's what Doctor Who really does. But again, when you look at all those, especially with Doctor Who and Star Trek, it is very much, okay, what could really happen? Star Wars is quite fantastic. And let's not even start going near Marvel, because that really is quite terrible. But, you have to be optimistic, and I try to be, unlike some astronomers who tend to try and bash astronomy. And actually, going back to the black holes example with Interstellar, it was really funny when that came out to see astronomers debating on Twitter like how the black hole physics worked, about time dilation. And it basically came about that one person who was really saying, oh, this is rubbish science, forgot that actually within the story, if you follow it carefully enough, they talk about how the black hole is rotating. And that was enough to explain everything that they said was wrong in the movie. And it's just like, then they had actually to say, okay, I was wrong. I missed that piece of the movie. So sometimes you have to watch really carefully.
Well, you don't have the time to do that, do you?
Watch movies?
Watch them over and over to get every single bit of information.
No, but then you just remember things like that. And you see other people pick up on it. But no, I have my favourite movies, and I watch Doctor Who a lot. I'm trying to get through all the Doctor Who's that I own on DVD. So I'm just going through Peter Capaldi's season now, and then I'll go back and start again at the beginning. But I'm taking a bit of a break from Doctor Who because there's too many other things on TV to watch.
Fair enough. So how much of your time do you spend analysing the sun? Because it is a star, right? So,
yeah.
So even though your study is on other, because every star, right, it would be different. It's not like every star would be the same. Every star would have its own unique structure to it. If structure is even the right word.
No, yes. I mean, I've got a textbook called The Structure and Evolution of Stars.
Okay, all right.
Because exactly, the structure tells you how hot it is inside, which tells that sets how quickly they're fusing elements in nuclear fusion. So that tells you how long they'll live for. And so in general, there's two parameters in a simple case that tells you how a star will evolve or what a star's lifetime will be. That's its composition. So the sun is something like 70% hydrogen, 28% helium, and 2% other stuff. Astronomers call everything that's not hydrogen and helium metal. So, carbon, that's a metal. Oxygen, nitrogen, all these things that aren't metals to a chemist, to an astronomer, British metals. And so that and the initial mass of the star sets what's going to happen over that star's entire lifetime. So another star like the sun with the same metallicity, same composition, and the same initial mass will evolve in the same way if they're single stars. A more massive star will evolve quicker and be more brighter. A lower mass star will evolve slower and so have a longer lifetime, because some stars can have hundreds of trillions of years of evolution before they die, whereas the most massive stars can die in about 3 million years. And so that's what mass does for you. The complications we've been looking at in Auckland are really what happens when you actually have a binary star system. So the things get really complicated, structures get really strange when you have two stars in a binary, because then it's not just one star just doing what it's going to do. It gets bigger, becomes a red giant, and then becomes a white dwarf. If you have a star in a binary system and it tries to grow and it's got another star in the way, it's like, could you imagine what would happen if the Earth and the Moon were orbiting around each other and the Earth suddenly got bigger? Because then the Moon, it would hit the Moon effectively. I mean, the Earth is not going to change in radius. But that's the model we can have, that, if you have two stars, it's like the Earth-Moon system, but they're stars. One can get bigger and it can get in the way of the other one and they can interact. And that's where, mass can exchange between the two stars. So the other star can get bigger. And the star that was initially more massive can become hotter and denser and less massive. And then that's where all the interesting things happen. And the problem with that is that rather than just making one model with one composition and one mass, you've got to worry about the mass of the other star, and then you've got to worry how close they are. Because if they're really close, they're going to evolve quite soon. If they were much further apart, they might never evolve or evolve just before they die. And so, trying to equate all these structures and then work out, do these match the observed stars is really complicated. And that's why earlier on I said, you have to make 250,000 stellar models just because there's so many to try and calculate. But to go back, how often do I look at the sun? As you can tell, not very often, because it's one star. But it's the first star you've got to check. Because, so this is the funny concept, that the sun is so close up, we can study it in such detail, we actually know a huge amount about it. And there's things we still don't understand about it. Whereas when we go and look at other stars, they're so far away, we don't know very much. And so they look really simple. But, if we could be that close up, we'd see them in as much detail. So every other star you're looking at is always basically linked back to the sun, which is why, we always measure things in terms of solar masses and solar radii and solar luminosities, because that's the one star that we know really well.
So if the sun was to disappear, how long would it take before we all died?
Which way do you want to die?
Well, you'd freeze to death, wouldn't you? So if it just disappeared, then effectively everything's gone. But how long would it take in terms of from the time it disappears to the time the Earth just becomes a frozen wasteland?
Well, would it? So the okay, I'm just trying to think of multiple things because there's a great series by Kevin J. Anderson called Saga of the Seven Suns, where this happens to a few planets, not to Earth, fortunately, but to a few other planets, and kind of like talk about how they're going to survive and what will happen if the sun dies. So let's just say the sun stops shining. It takes 8 minutes for light to get from the sun to the Earth. So we'd have about 8 minutes. Although, here's a complication. So the energy being generated in the center of the sun takes about 100,000 years to get to the surface. So you're actually looking at stale sunlight. But if you were to turn off the nuclear reactions at the center of the sun, you'd have 100,000 years, or probably a bit more than that, before you'd see anything, because the energy would still be coming out from the center of the sun to the surface. So that's quite good. But if you just take away the sun, then you've got 8 minutes.
Wow. Okay. So even if it disappeared, there'd still be some sun there that would still. Oh, that's mind blowing. That it's stale sunlight that we're getting.
Yeah. So if you just stopped the nuclear reactions, you'd have 100,000 years. If you took the sun away, so it wasn't there anymore, which I'm not sure how you do that, but we can worry about that later. Then you'd have 8 minutes. But of course, the Earth is actually also geologically active. So there's heat coming from outside. From inside the Earth. And so most of the Earth's surface would freeze, but if you go down deep enough, you'd have enough heat or warmth to be able to survive in some way, assuming grow food.
So if you wanted to survive, you'd have to find a way to dig deep down into the ground within 8 minutes. Or you bury near the crust well before that to prepare.
Yeah.
Which I wouldn't be surprised if someone's already done, considering apocalyptic people.
Yeah. Or just go to Rotorua because they have the thermal springs down there, right? So we still have to move to Rotorua. Sorry, everyone.
So, talk to me about gamma ray bursts and how they work.
Yeah, we'd like to know. Well, for a long time we didn't know. Shall I start where everyone always? If you go to a conference on long gamma ray bursts, the first talk always has to do this is how we discovered long gamma ray bursts. And it was from American satellites which were sent up to orbit to find nuclear weapons tests in space. So, they were expecting to see terrestrial sources from the Russians sending nuclear warheads up into space and exploding them. Didn't see any of those, but they did see these bursts of gamma rays. And because they had multiple satellites, they could actually work out they were coming from outside the solar system. Because if you have three of these satellites, they all detect a burst. They're so far apart, the timing at which they would see the different events tells you where it is. And they knew it was somewhere out in the distance. So of course, this was actually classified information for quite a few decades.
Why?
Because it was nuclear weapons test satellites. So so this is always the problem with astronomy. There's a lot of history where it's linked to defense research. So it's makes you sit down and worry about ethics a lot. Anyway, we then started sending up actual X-ray telescopes, and they just detected these bursts that would last anywhere from like a fraction of a second up to several seconds. And it is just a burst of gamma rays, which is a bit bizarre because, gamma rays we normally think about, we don't really use them apart from in certain types of medical technology for imaging where, because they're such energetic photons, they're really quite dangerous. So they're like X-rays, but even more so, even stronger. And so that's why, radioactive elements are so dangerous, because these gamma rays, if they hit you, they will go deep inside your body and cause damage. But not to worry, because these gamma ray bursts are actually so distant, they're not going to affect us. We're quite safe. We can just detect them and these bursts of gamma rays. But as they started building up this knowledge, we didn't know if they were within our solar system, within our galaxy, or if they was more distant. Because if you work at how many gamma rays you get, and if they were in our galaxy, they would be quite faint. They wouldn't be anything special. If they was much more distant in other galaxies, then they had to be some of the brightest explosions known. So they had to be outputting something like 10 to 100 times the energy that our sun will do over its entire 10 billion year lifetime in a few seconds. That's how much energy these things were thought to produce. And when they started building up the sample, they realized there's two sorts. There's ones called short gamma ray bursts, and there's ones called long gamma. Astronomers love to do this. We love just to take a population of something and say, okay, these ones are the short ones, these are long, these are type 1, these are type 2. We never learn our lesson. It's pretty bad. Because there's things that belong in both camps, because you can have short, long bursts and long, short bursts. It gets very confusing. Anyway, so we know that the long bursts, eventually they were associated with galaxies. So we had the problem is you see these gamma ray bursts, and so they're only there for a few seconds, and then you've got to turn your telescope to look in that direction within a few seconds to see if you can see anything else. And I think it was somewhere in 1997, we did this for the first time and found this afterglow. So it wasn't just a gamma ray burst, we got to see the optical light coming from whatever had exploded. And then we were able to see, oh, that's in a galaxy. And we started getting more and more of these, and we realized they're actually just going back to those supernovae I talked about, where you've got a star that's more massive than the sun, dying. Some of them produce these gamma ray bursts when they die. And after much theoretical work and much other observational work, we know what actually happens is these stars, when they die, are really rapidly spinning. They're spinning so rapidly. I mean, our sun rotates about once every 25 to 30 days. These things must be rotating like once a day, which is really rapidly. So when they form their black holes in the center, all the material is spinning around it. And so you get secretion disk around the black hole, and it forms two jets that come out and explode out. And those jets, because that's material being flung out along the poles, rotation axes of the black hole, it's going fast at the speed of light, so close to the speed of light. And so they look really, really bright, but in effect, it's just a normal, boring supernova just exploding in a dramatic way.
Right. So what's the area that it usually covers in terms of like the circumference? How
What, the jet?
What? Or, yeah. Well, the burst, the actual explosion itself, right? How much area does it cover?
So the entire star would just explode generally in a supernova, which go bang. Whereas the jets, that's one of the things we don't know. So when you're trying to work out the number of these events, right? Because you're a jet, and you can only see them as gamma ray bursts if you look right down this jet. If the jet is 1 degree, then you must have like many more of them. If the jet's quite wide, say 10 degrees opening angle, then you see a few, but you're seeing quite a lot of them. And of course, if the jet was 45 degrees, you're basically seeing half of them. But we think the jet angle is somewhere between 5 to 15 degrees, but it varies between different gamma ray bursts. So it gets very complicated trying to understand these, and then trying to actually also work out what is the angle, right? So if my is the jet coming directly towards me, or am I seeing it off by a small angle? And so that's kind of some of the stuff we're trying to work out. And it's difficult.
Would it ever be possible for one to be like right by the Earth, like for it to take place right by the Earth?
Yeah, so this is something that, so my colleague I mentioned earlier, Elizabeth Stanway, has done some of these calculations. So she did a really nice paper a few years ago, which was, when did galaxies become habitable? We always think about around stars about a habitable zone where a planet can have liquid water like the Earth. Whereas, within a galaxy, when would enough supernovae or gamma ray bursts or other things happen that would kill you, or wipe out all life on the galaxy? Because so actually, when she did the calculation, it was about 5 billion years ago, and the sun was formed about 4.5 billion years ago. So one of the reasons we may be here is because the galaxy became habitable enough, because there aren't enough gamma ray bursts going nearby, and there are probably no gamma ray burst, what I would term progenitors, within our galaxy, because the composition is too high. When we look at where the galaxies where long gamma ray bursts happen, they tend to happen in smaller, lower mass galaxies that have much less metal. And why is this an issue? Well, one of the reasons, I'm trying to think about how to describe this. So you need to have a star that's rapidly spinning, right? And if it's rapidly spinning, it will throw out material just because, it's like if you're spinning yourself round and round and you're holding on to something, eventually you're going to let go and it's going to fly off. And so as you lose more material, you slow down. And one of the things that low metallicity does is it makes it very difficult for a star to lose mass and slow down. So you have to have those very low metallicity small galaxies to be able to have these stars that get to the point where they can experience gamma ray bursts. And they're very, very rare types of explosions because of all these things you need. It's like what you said before, you've got to go through. The longer you evolve something or try and understand what's going on, the more and more errors that come in. It's also the things that there's more and more things that can stop something from happening because they sort of add up over all that evolution. So to get to a gamma ray burst in a galaxy, I'm not going to say it's impossible, but it's very, very rare and there shouldn't be any. Whereas we know in some more distant galaxies, we can see that because we know the rate of gamma ray bursts with local universe is much lower than it was, say, about 10 billion years ago.
So, with a shooting star, is the star actually going that fast, or is it a combination of the star and because the Earth's moving at the same time?
So, my cousin asked this very question when I'd just done my PhD. I had a party for my family and explained to them my PhD thesis. And I said, "Go and ask me any questions." And my cousin Debbie said, "No, what's a shooting star? Because it's not a star." So that's the confusing thing, right? So
why is it called a shooting star if it's not a star?
History. Right. So we didn't know what they were, right? So the stars were the things up in the sky. Most of them don't move. And actually one of the things that if you look at the history of astronomy, not one of the things that held us back, but one of the things that slowed down advances and like working out that the Earth went around the sun was the fact that the stars didn't move. So if there was a star close enough, and as the Earth went around the sun, we would see it moving slightly due to parallax. All stars actually do this, but you just need to measure the very, very small angles. And so we now have these satellites that can measure something like even billionths of a degree in angles to be able to see all these other stars moving on the night sky as the Earth goes around the sun. So most stars, though, don't move very fast at all. Planets do, but they're called wanderers. That's because they're orbiting around the sun the same as we are. But shooting stars are just these bright lights that look like a star, but they move quickly, as you said. And that's because they're actually fragments of meteors or comets that have come into the Earth's atmosphere, heated up, and they're just vaporizing because they're going so fast, because they are going fast. They're just basically the Earth is coming around and their velocities relative to each other are fast enough that the thing heats up, glows brightly, and so we see it's a very hot object. And we know that there are some things called meteorites. So a meteor or a shooting star is what you see in the sky. When it hits the ground, that's a meteorite. So does that help?
Yeah, that does help, but I still don't understand why it hasn't been changed. If we've learned so much about science and space since then, and it's technically not a star, why hasn't the curriculum been updated?
But how do you change it, right? Because you would still, it's what's one of the first songs that people learn about stars at kindergarten? What's the song?
Twinkle, Twinkle, Little Star?
Twinkle, twinkle, little star, how I wonder what you are, right? So why has nobody stopped that from being sung in kindergarten? Because we know exactly what a star is. Because humans are complicated, right? We can sit here all day talking about how wonderful the universe, how complicated it is. But, Twinkle, Twinkle, Little Star is a song we all learn. And it's part of being human is to learn that. Which is also why when I talk about stars in our first year astronomy course in Auckland, I always go, twinkle, twinkle, little star. I know exactly what the swear word you are. Because we do know, right? And there are versions of it. You can search on YouTube for astronomically correct twinkle, twinkle, little star. And there's some great ones out there. And my only answer is, if you go through astronomy and you look at why we measure the things the way we do, there's many things about them that just go, why? Why did we do this? And part of the problem is history and just to do with the way that humans work. So, I'm sorry.
No, that's all right. But wouldn't that result, I mean, astronomers then, like yourself, would probably end up getting into philosophical questions, right? You must have so many questions all the time and question everything.
Well, when I was a PhD student, I didn't, because I was just studying the science. But when you start teaching it and you're trying to teach broad astronomy, I mean, I never took a broad astronomy course. When I was studying at university, the astronomy was very much, this is how everything works. Whereas I now have to teach this Astro 100 course where you're trying to give an introduction to people about everything in the universe. And, one of the things is when you're trying to teach that, you need to go back into the history because it's useful to understand where these things come from and also realize, that the things we're trying to teach people are difficult. And talking about the people who came up with this to begin with is helpful because it makes you realize somebody had come up with it. It wasn't always just, it's difficult to try and understand what's going on. So, yeah, but people don't talk about astronomers of ethics. So we've got a really good question at the moment with the mega constellations that are going out. So you have different groups around the world, for instance, sending up microsatellites or CubeSats to get internet everywhere you are by linking into a satellite, which is a problem because then, that's not going to be shooting stars. They're actually really visible to the naked eye. And people have already posted images on YouTube and Twitter and social media saying, oh, look, all these wonderful constellations, but they're stopping you from being able to see the night sky. And for astronomers, they're terrible. So it's not so much philosophical questions, it's also an ethical question around, you have to start thinking more broadly. And actually, it's the good thing about now I've been doing this so long, I can think about those questions much more deeply. So, yeah. But in terms of philosophical question, we always try and sit around and think about where do we come from? That's one of the biggest philosophical questions there are. And I can answer half the question because I know from stars make the elements. And so I can know that, iron comes from the iron we need for our blood to be able to carry oxygen around our bodies, comes from stars like our sun and binary star systems that have exploded, whereas the oxygen we're breathing comes from massive stars that are exploding, right? So that tells you where the elements that make you come from. Where did the universe come from in the Big Bang? I can't explain that. Nobody can. And so that's another philosophical question. You end up sitting there going just give up.
This isn't really related to stars, this question, but I am interested to get your view on Elon Musk's mission to get people to Mars. How feasible is it? Given that how we interact with the Earth, and wouldn't it affect the way our body is formed and works if we're on a different planet with different gravity?
Yeah, we're really evolved to be on this planet, right? We're evolved for 1G, 1 atmosphere. That's why they're 1G. That's why they're 1 atmosphere, because, it's like we use 1 solar mass, 1 solar radii. So, the funny way to answer this is that a few years ago, I got invited to write a book for Doctor Who called Doctor Who in Science. And it's like all these different chapters by different scientists about different aspects of Doctor Who science. So one of those is looking at Doctor Who and how, do they go to alien planets or do they go to Earth-like planets and stay on Earth? Because, for somebody who can go anywhere in space and time, Doctor Who spends an awful lot of time on the Earth. And, between the two series, the old and the new, we actually, in the old series, never knew about planets around other stars. And then when the new series came on, we actually started finding planets around other stars. So you'd think in the new series, they'd go to Earth-like planets more. They don't. They actually stay on Earth more in the new series than they did in the old series. But one of the things I talked about this is looking in Doctor Who episodes, you can see where they've done this kind of thought experiment. So they've done the episodes where, you have colonists on another world, and you have all these competing demands, like indigenous life, from industrial, mining concerns, as well as from people who just want a new home, somewhere new to live on their own. And this is one of the issues. It's in the future with high technology, you do that. But there was this issue around food with these colonists. They weren't able to grow crops, I think, if I remember correctly. So the question is here, if you send people to Mars, even if those people you send are fully fully informed about all the risks, what they're taking, is it still ethical to send them there? Because they may die. But for all the reasons you've just said, their health may be severely impacted. We don't know what they're going to do. Is it a one-way trip, or are you planning on bringing them back? Because I know there was one person, and there was some group once that was going to say, no, it's a one-way trip, you go there. It's just like some people say, I want to go. It's just like sending someone to their death on another world. That's something I think that people need to have a conversation about, because then, it just becomes very difficult. So it's possible, and we can do it with modern technology for a short period of time. Long-term habitability of Mars is probably not possible for a number of reasons, but I have seen some really fun things people come up with, like, how to give Mars a magnetic field. Basically, you have to mine Olympus Mons, turn it into superconductor, and you make a cable that goes around the equator of Mars, and you can give it a magnetic field. So there's all these things we know we can do, but it's just in terms of developing the technology, which is money and time. And then you've got how do you feel about sending someone to their most likely death?
Well, it just seems like it's the ultimate guinea pig project. Like, you wouldn't really know until you sent them there, and then you study what happens to them, and then you'd definitely know.
Well, we know, because, we've sent people to the space station for a long time, right? So there's many different ways that space can kill you. It's great. It's space is unceasingly hostile. No horror movie actually even just shows that. Even like Gravity, I think the movie with Sandra Bullock didn't even show how nasty space was, and it showed that space was pretty nasty. If we wanted to do it, we'd have to go to the moon first. Right? So the problem with Mars is it takes you about 700 and something days to get there, if I remember correctly. There are fast orbits, but it depends how you put together your spaceship and what technology is available to get there. Whereas with the moon, it takes about 3 days to get there. So if anything happens, you can come back. And the moon and Mars, the moon has a bit lower gravity, but if we put people there and they can survive for long enough, then we can go to Mars. But again, it's like there are rules against using humans as guinea pigs, right? I'm pretty sure they're somewhere if I go and look them up, because we're not allowed, because the people who did that in the past, experimented on humans, are not good people. And everyone seems to ignore that fact just because you're going to Mars, but that's a really horrible guinea pig experiment, I think. I want to do it. I think we should go to Mars and other planets and explore the solar system, but let's do it in a safe way.
So have you seen the movie The Martian?
Yes.
I've I read somewhere actually that a lot of the science in it is actually quite accurate, save for a few things. Yeah. No, the book's really good as well. And so a lot of things, there's some things, I think, like they want to stop the spaceship by evacuating the atmosphere inside the spaceship. That's rubbish. But the rest of it's pretty good. Yeah. So there's actually loads of movies where they've gone to Mars, and every time you see them, they're always, apart from the one with Val Kilmer, which I can't remember. That one's terrible. But all the others are pretty reasonable. Because the spaceship they design is the kind of spaceship you would have. You would have to have some kind of centrifugal device, so they have Earth gravity, or at least some form of gravity during that 2-year mission to get there and back. And you would have a lander that goes down. You'd have to have a habitat, because you're going to spend there months if you go there, because you don't just spend a few days. Because when you go on holiday, you take maybe several hours to drive there, then you spend a week and drive back. It's the kind of thing that you have to think about if you want to go for a longer time, rather than just pop in and pop out like we did for the moon. I want to go back to the satellite thing that you mentioned before. So if a star, would it be possible for a star to kind of collide with a satellite and then cause a chain reaction which causes all the other satellites to crash into each other? We've already got a problem with space junk.
Yeah. So that's a good question. I think most meteorites or comets, when they come in, would probably be too small to affect. We know that satellites do have what we term micrometeorite damage, because a lot of meteorites are actually just dust. If you wanted to find out how much dust, a meteor of dust comes down on the Earth, you can go up to the gutters in your house, dig out some of the dirt, and if you get a magnet, put the magnet in a plastic bag first and hold it up to dirt in your gutter. You'll get magnetic dust. And that's because that's like metal meteorite dust coming from space and is raining down on your roof. And it's actually quite a lot of it. But space is big. So in terms of a meteor causing that kind of collision, that is very, very unlikely, because the big meteors that would do that are very, very, very rare. However, if two satellites were to collide, then we get into a problem, because this actually is an effect, and I can't think of what the effect's called. But basically, if two satellites were to collide, they would produce all this other debris that would go on and then cause more and more collisions. And so, as you suggested, you would then basically have loads of collision debris in a low Earth orbit that would take like centuries to actually decrease. And so you wouldn't be able to go through it because the risk would be too high. And so we're actually approaching that point now when we've really got to start thinking about space debris back down much more quickly, because if we hit that effect, it will affect any satellites we put into low Earth orbit.
Is it just satellites that it would affect, or would there be other things that would be affected by it as well?
Or anything that would have to go through that, when there's nothing else up there apart from satellites.
Yeah, I mean, well, you couldn't go to Mars, could you? Because it would hit debris on the way up. Yeah,
that's the problem. You wouldn't be able to get through it unless you had like an armored space shuttle. But then it's let's not have to go that far. It's probably the best thing.
Because how would you bring? Is there any way possible right now to kind of bring the space junk? I mean, there's already space junk up there. Is there any way to bring it back to Earth to have it kind of burn up in the atmosphere?
Yeah, so there's lots of people developing technology now. So my colleague Nick Grattenbury in Auckland and John Cater are part of the Space Science Institute we have at Auckland, and they're actually looking at some of these problems. And they're trying to launch cube satellites. And one of the things is that you have to have a plan on how you bring it down. People are starting to wise up to this. So one of the things is if you put something up, you've got to have a plan for either how you get it down or you make it safe. So that's a pretty good step. And so that's the first thing of actually trying to like think about, okay, I'm going to eat this banana. Isn't there a bin nearby before I start eating it that I can throw away the banana peel? That kind of thing. But other people have got, there's many different technologies. There's one that's like, I think there was one satellite that had 3 different things on. And so one had a net that would actually go and like you fire the net and it captures it and then you pull it in and you deorbit the damaged satellite. Another one had a harpoon. And I think another one just had like a sticky something that went over and stuck onto the other satellite. So there are ways of trying to do this, but it's kind of, why did we not think of a way of bringing it down beforehand? Because it's cheaper just to like get rid of it when it's died rather than worry about it just because it's up there. And I can't remember, but it's like there's thousands of satellites up there and they're increasing all the time. So people are developing those technologies.
Would there be any way to beam light from satellites? So say the sun, obviously his rays hit a satellite, the solar panels. Is there any, well, I don't think there is, but is there any way in the future that could possibly find a way to beam it back to Earth?
Wasn't that the theme to Diamonds Are Forever and Die Another Day, the James Bond movies? In both cases, the supervillain was trying to make something to do exactly that, and it wasn't a good ending. In case you don't remember,
it is a film though, so I don't know how realistic it would be. And I'm talking about the good reasons, not the psychos that want to use it for nefarious purposes. So transmitting power wirelessly is really difficult. So I remember seeing something recently where somebody reckons they've done it, but when you look at how you transmit energy by electromagnetic waves, there's a reason we use cables everywhere, because that's a really good way of making sure the energy goes down. Anything else, if you're just trying to beam it, it doesn't really work. But I mean, also, it's just when you look at the economics, why would you build a solar farm up in space when it's cheaper to actually put solar panels on the ground? So at the upper end of the Earth's atmospheres, if I remember correctly, each meter square of area gets about 1,000 watts of energy from the sun. If you come down to
Down to ground level, it's about 300 watts per meter squared. So you're only losing the atmosphere about a third of the energy. And so, you know, how big satellites can be, and you're trying to think how much bigger you'd have to make an area on the ground, you'd only have to make it like 3 times as big as the solar panels you'd have in space. And one of the things is it's much cheaper to do that on the ground because you don't have to launch those solar panels into space, which are also quite delicate. So yeah, I have read of this concept, like you see it's like solar collectors in science fiction, but it's like you would never do that.
So do you every day like look through a telescope up at the stars at all? And do you ever do that, or do you or have you ever looked at any stars recently and it has unique properties that resemble like nothing you've seen before?
So this is always one misconception about astronomers. Whenever, like, I used to see it a lot, where you know, you'd have some news story about astronomy, and they would go and interview the astronomer in question, and they would have to say, "Okay, we need you to look for a telescope so we can take an image of you. Just doing your astronomy." And it's just like, yeah, we don't do that. And what's worse is the pictures are always, or little video clips are always during the day. Right, so you can't look. I mean, you should never look at a telescope at the sun, because that would just actually fry your eye and make you go blind. So you know, you never look at a telescope during the daytime. And all the big telescopes, you know, you use CCD cameras at the back of the telescopes. But for me, it's even worse than that because I'm a theorist. So so there's the like observers and there's theorists. And observers, they go and make the observations using all the different telescopes around the world, reduce the data. Whereas I try and do the other way. I put all the physics into the computer and work out, can I make a synthetic observation that looks like what the observers see? Because then I understand all the physics. But, you know, the really exciting thing that I've been doing over the last few years is, you know, just talking to different observers, because they end up coming to me and going like, Jan, we find this thing that's really funny. There's this really weird binary star. We don't understand it. Can you tell us the evolutionary history of this system? So there's a few Wolf-Rayet stars that someone, Noel Richardson from the US, has come to me about, because they're in a binary system and they can actually resolve the two stars going around each other. I mean, this is very difficult. You've got to actually use a special type of telescope to get really high resolution images to actually see the two stars orbiting around each other. And so they know the types of stars, they know their masses, which is really important because, you know, that's what really sets their evolution. And then we can search through our models to try and work out where they're coming from. And, you know, there's always these pictures that people have had about these stars for a long time. But what these binary stars are telling us is that may not be the complete picture. And so that's the really fun thing. It's like seeing these unusual properties and then actually trying to work out where those stars come from. But there's so much observations because there's so many observational astronomers. Trying to understand them is now what many people are trying to do, because, you know, we do need more observations. People always say we need more observations, but there's still stuff we need to do to try and work out how these stars actually evolve, what they actually are.
Do those two roles ever overlap, though, with a theorist and an observer? Or do they kind of just go their separate ways? Well, do they ever overlap? Like, do you ever go out in the field? I mean, not out in the field as in out to space, but you know what I mean.
Yeah, I had the opportunity, but I've never had a chance to. I mean, and in Auckland, we do have Stardome. And so I've gone there a few times and actually looked through their telescopes. You know, in New Zealand, it's really interesting because we have a really strong, I almost don't want to call them amateur astronomers. They're like professional amateurs, right? Because
what does that even mean? A professional amateur?
Yeah. So, you know, they have telescopes that are big and they're taking research quality observations, but they're not a paid employee of, like, they're not employed to do astronomy. They're doing it for their hobby.
Right.
But but they're doing it at such a level, and, you know, some of them have PhDs, some of them have master's degrees. They're doing it at a very high level and are part of collaborations. So within New Zealand, there's actually a way of detecting planets around other stars called microlensing. And you can do this astronomy with small telescopes that are like 30 or 60 centimeters across. But you need high cadence observations. And so when an alert goes out that one of these microlensing events is happening, people around the world, especially in New Zealand, go and observe them to help get the light curves, because you might get on a paper that discovers a planetary system around another star, which is quite exciting. But, you know, being a theoretical amateur is quite difficult because you have to really think and do a lot of work that isn't necessarily interesting. It's not looking through telescopes. And so there is kind of a divide. And you always hear like observers talking about, how, I should never believe a theory until it's confirmed by observation. And actually, that's the scientific method, right? You put a hypothesis forwards, you predict something, go and test, see if you can observe it. If you don't observe it, then you need to change your hypothesis. If you do observe it, then you know your hypothesis is correct, and so then you can go on improving it by like making it better. Whereas I should always say, don't believe an observation until it's been confirmed by theory as well, right? Because you can see something, you think there's much you don't know, because these stars are also distant. If you see them, you don't know everything about the star, but in the model, we understand everything about it. And so there's always this tension between theorists and observers. But it can also be really good fun because there's also a lot of space where it's just, okay, how can we work together? So while I was a theorist during my PhD, my second postdoc was in Belfast, working with an observational group, which was kind of difficult because then I finally understood what observers do. And so then I could observe my models observe my models like the observers do and actually get really close. And so we actually made all these advances because we came together. And it's really funny because my current postdoc, Eloise Stevenance, came from an observational background and has come over to a theoretical group. And so she's in the middle as well. And both me and someone else are writing her references, and I'm calling her a theorist. No, I'm calling her an observer, and the other person's calling her a theorist because the other person's an observer and I'm a theorist. And so we're seeing qualities and so all the future observation, all the future discoveries are going to come from these people that are actually in between these fields. And it's the only way we can. And that's probably for all science. You've got to work together in that.
Wow. Okay. That's fascinating stuff. I know you got to get going, so I'll ask you one last question. Just because it's a good segue, I feel, since we're talking about theories. If I run into a flat Earth theorist, how do I rebuttal them?
So if they believe in a flat Earth, they're just denying evidence. Right. And so this is always, what trusted evidence, what trusted knowledge is there? And that's always a problem because we know you can go to Rocket Lab, you can see their live streams from the launches, and you can see the Earth looks pretty damn spherical because they take off, they have the live feed, and you're going all the way from the ground, it gets very small, and then you can see the curvature of the Earth. You can also look at lunar eclipses, and the shadow of the Earth on the moon looks really spherical. You can Skype someone in the UK right now, and it's nighttime. So there must be different things. And whenever they try and deal with things mathematically or reach out to people for mathematical help to try and understand flat Earth, the reason they want to do that is because they don't want to break the symmetry from flat Earth to go to spherical, because that's the one thing that naturally explains all the observations they're trying to explain. But there's things like weather systems. We only get the weather systems that cyclones or move and rotate because the Earth's rotating and it's spherical. The other thing you can say is just watch a ship through binoculars as it sails away, and the last thing you'll see that disappear will be the mast. Because, as you go around the curvature of the Earth, as the boat sails away, it gets to a point where the boat is below the horizon, but the mast will still be above. You can even look at beaches in the far distance, like a way across the Waitemata Harbour, just to try and see if you can actually see that difference. I haven't checked it myself, but that's one thing you can do. So the way to try and do that is you can suggest all those things, but even if you suggest all that evidence, they're still going to say no because they've got to a point. And this is one of the huge problems we all have around, everything to do with vaccinations, all types of rights and everything else. It's just that people deny evidence because they go down a thing, and it's how do you help people evaluate the information and actually see what is true and what isn't true. So, that's a difficult question.
It is, and it's a long one too. So I'll wrap up there. Thank you so much for this. There were heaps of other questions I wanted to ask you, but time is always of the essence. And I know you're a busy person, so thank you for taking time out. If anyone wants to follow your work and what you're doing and all that, where can they go?
Twitter is always the best place, astro_JJE. Or you can find me on Instagram as well. Although that only selfies get posted to Instagram. My work gets posted to Twitter.
How come you don't post it on Instagram? Your work?
Well, because it takes too much explanation. I suppose I should put up more pretty pictures.
But what's that?
Because I do have there's no things.
But what's that saying? A picture is worth more than 1,000 words.
Well, no. According to the journal I've just written for, a picture is either, if it's a large picture, it's 600 words. If it's a small picture, it's 300. They have exact values. But no, that's a good point. I should probably post more of my science plots to Instagram. Yeah, you're right. I'll try to do that.
Okay. Well, hey, Jan, thanks again. That is the show, everyone. Make sure you share, like, and subscribe. Support Jan and everything that she'll be doing in her future endeavors. Thank you again, Jan. I appreciate it.
You're more than welcome, Reece. Thank you very much for inviting me. It was good fun.
Yeah, likewise. All right. See you later, everyone.